and 6 now, which is conservative and non-conservative forces. These forces affect energy. Remember, energy is always conserved in total. Energy can only be transferred, we cannot create it, but in this section we are only concerned with with mechanical energy. So first we've got to say, what is mechanical energy? Mechanical energy is the sum of the kinetic and the potential. So it's only potential and kinetic, very, very important, because those have to do with motion. Mechanical energy is EK plus EP. It's the sum of those two together. Remember, EK is a half mv squared, EP is mgh, h being the vertical height. Now, the principle of conservation of mechanical energy says to us that the total mechanical energy in an isolated system remains constant. Here we need to be careful because it's got to be isolated. So we get non-isolated systems. You know that. We've worked with isolated systems before now. But for mechanical energy, kinetic and potential to be conserved, in other words, potential and kinetic change between each other, the system needs to be isolated. So what that means for us is the potential plus the kinetic at one point would be equal to the potential plus the kinetic at another point. Okay? Doesn't matter where those points are, it's in the same motion, but there's no external forces like friction. That gets us to what is a conservative force. Now, a conservative force is a force for which the work done in moving an object between 2 points is independent of the path taken. Gravity is a conservative force. Okay, mechanical energy is always conserved with gravity. It doesn't matter how an object falls, for example, 12 meters. It could have gone through a roller coaster to have fallen 12 meters, or it could fall down 12 meters vertically. It doesn't matter. The mechanical energy change is the same. So we get the fact that with gravity, it doesn't matter how the object gets from one point to another in a gravitational field, your mechanical energy will stay the same. Okay, your total mechanical energy. Non-conservative forces is a force for which the work done in moving an object does depend on the path. Now, this is important. Friction and the applied force are non-conservative forces. When you have an object that's that is experiencing friction, the longer the distance that it experiences that friction for, the more energy friction will take out of the system. So the length of the path is really important. We don't care about the direction the path takes, we care about the length. Same with the applied force. So what's important is that a non-conservative force means that mechanical energy is not conserved. Generally, it means that we will lose kinetic energy to the surroundings, and that kinetic energy will become heat, sound, maybe even light. Okay, but mainly heat because we're looking at friction. Good idea. Please do activity 1 on page 171. The memo is on Teams. Conservation of energy calculations. Well, mechanical energy of an object changes if a non-conservative force does work on it. So the change in the mechanical energy is the work done by the non-conservative force. Change in mechanical energy means EK has to change, and so does EP. NC stands for non-conservative force. Most of the time, that non-conservative force will be friction, but applied forces are also non-conservative forces. Friction takes kinetic energy out. Applied forces usually, not always, usually put kinetic energy into the system. Okay, so let's look at an example. A cyclist is freewheeling. Freewheeling means that she's not pedaling, she's not applying a force forward, she's just allowing the bike to move. along a horizontal surface at a constant speed of 10, which really means this first surface is frictionless because it's physically impossible for her to do that otherwise, but we're actually not concerned about the horizontal part. She reaches the bottom of a ramp at position A that has a height of 1,2 meters. The length, the 8 meters, is delta x. This 1,2 meters is for potential, okay, because that's how her potential changes. While freewheeling up the ramp, she experiences a frictional force of 18. So while she's on the ramp, there's now friction. The total mass of the bicycle and the girl, 55 kilograms. So, explain whether mechanical energy is conserved or not as she moves from position A to B. Ignore the typo there, sorry. Well, from A to B, there is friction. Friction is a non-conservative force, so mechanical energy cannot be conserved as friction is present. You have to explain it, and it's a non-conservative force which will dissipate energy to the surroundings. Energy gets lost to the surroundings, okay? I know I'm going really fast. If you need to, pause the video and make sure you get all the answers, all right? Calculate the kinetic energy of the cyclist at position A. Well, that was nice and easy because that's EK, and we know EK is a half mva squared. We know M, we know V. Straightforward substitution, nothing difficult, and she has 2,750 joules of energy at position A. This is before she goes up the ramp where now there's friction. Then they want the kinetic energy of the cyclist at the top of the ramp, okay? This, because there's a change in kinetic, you've got to remember that WNC, I'm not going to use NW, I'm not going to use work net here. The non-conservative force is friction. Friction is doing the work. I know that work done by the non-conservative force is the change in EK plus the change in EP. And there is a change in EP. She went up a height. So, we're going to look at the change in EK. B minus A, B was her final position. B minus A, B was her final position. Substituting in what I know, friction was 18. Delta X is 8. Friction acts at 180 degrees because it's in the opposite direction. EKB is what I want because I want the kinetic energy at B, not the velocity. I know the kinetic energy at A. We just worked it out. Potential at B, mgh. Initial potential is 0 because she started at the bottom of the ramp. Okay, so she has no height. All we're doing is solving for EK. And we get 1,959,2 joules. All right. Smaller because there was friction. That energy has changed into heat from the rubber on the road. Okay. Then they want you to calculate the speed of the cyclist at B. Well, I know the potential at B. Therefore, I must be able to work out the energy. Well, the V at B. Okay, EK at B is a half mbb squared. We have 1,959,2, which is then a half times 55 times VB squared. Don't forget to square root your answer at the end. 8,44 meters per second. Okay, really not so bad. Do the activity. As you can see, the answers, the memo is in Teams. You can go find the memos there.